Welcome to our second lecture on thermodynamics. In this lecture, we'll ease our way into some of the important history of thermodynamics and discuss some underlying concepts which will help set the context for the course. By the end of this lecture, I'd like you to have a good grasp of the following concepts. First, the structure-property-performance triangle. Second, the difference between a macroscopic and microscopic view of the world. And third, some of the key historical milestones of thermodynamics. Now, most of us are familiar with at least some of the various archaeological ages of human civilization, from the Stone Age to the Bronze Age to the Iron Age to the age of plastics and recently what many consider to be the age of silicon. Notice that the way we like to define the time periods of human history correspond to a given material. In fact, humanity's ability to thrive throughout history has often relied upon its material of choice, and importantly, the properties that this material possesses, or I should say that humans figured out how to control. In most of human history, it took centuries to master a particular material. For example, the iron that appeared just at the end of the Bronze Age was quite inferior in its salient mechanical properties to bronze. In fact, over a whole lot of time and trial and error, people realized that iron could be made to be many things. It could be weak, strong, ductile, or brittle. It all depends on where you are in something called the phase diagram of the material. This phase diagram is a kind of map. And much like any map, once we learn how to read it, it unlocks important knowledge. In thermodynamics, a phase diagram provides the key knowledge to predict what material you've made and what properties it will have once you've made it. Let's take a look at how our ability to create these kinds of materials maps, these phase diagrams, came about. You see, for centuries, even millennia, engineers recognized that properties of materials were determined by their nature. What I mean by nature here is the composition of the material and what it looks like, what's in it, how do those things that are in it come together, and what structure do they ultimately form. Now, these engineers saw that the nature of a material could be intentionally modified or controlled by processing it in an appropriate way. If they heated water, for example, they could repeatedly make it boil. If they banged on a piece of metal, they saw that its mechanical properties changed and could, in some cases, get even stronger the more they deformed it. Different materials melted at different temperatures, and mixtures of materials would have different, sometimes surprising melting points. But for all of these wonderful observations about the way materials can be engineered by processing them in different ways, the rules that were derived over thousands of years were entirely empirical. In a way, a materials engineer resembled more a master chef than a modern technologist. Recipes were passed on from engineer to engineer, from generation to generation, to be memorized rather than understood. It took a long time after the Iron Age for this to change. Although still more than 400 years ago, way back in the 1600s, a great advance was made by the German scientist Otto von Guericke. He built and designed the world's first vacuum pump in 1650 and created the world's first large-scale vacuum in a device he called the Magdeburg Hemispheres, named after the town for which Otto von Guericke was the mayor. Now, why would someone want to build a vacuum pump? Well, for literally thousands of years, since the time when Aristotle famously claimed that nature abhors a vacuum, people had been trying to create a vacuum to see if that statement was really true. Guericke's goal was to disprove Aristotle's long-held supposition. The Magdeburg Hemispheres that Otto von Guericke designed were meant to demonstrate the power of the vacuum pump that he had invented, and more to the point, the power of the vacuum itself. one of the two hemispheres had a tube connected to it with a valve, so that when air was sucked out from inside of the hemispheres, the valve could be closed. The hose from the pump detached, and the two hemispheres were held together by the air pressure of the surrounding atmosphere. In one demonstration, back in the mid-1600s, Guericke used 30 horses, 15 of them attached to each hemisphere, and trying as hard as they could to run in opposite directions. No matter how hard the horses pulled, they could not pull the pieces apart after the vacuum was set up. This was quite a demonstration of the power of the vacuum. Now, that phrase itself was one of the misunderstandings that Guericke helped to clarify. That is, it's not the vacuum itself that has any power, but rather the difference in pressure across the boundary which creates the power of the vacuum. What we are really witnessing in the hemispheres experiment is the power of one atmosphere of pressure, which is pushing on the two hemispheres to keep them together. This pushing force is due to the pressure difference between inside and outside of the sphere. Let's take a first-hand look at how powerful indeed the creation of a vacuum can be. We're not going to be bringing horses into this studio here, but I've got a smaller horse-free demonstration of the power of the vacuum that I'd like to show you now. Okay, so as I promised, there are not going to be any horses in this demo for me to show you the power of the vacuum. Instead, what I'm going to do is a pretty cool trick that almost seems impossible. And all I need is an empty bottle and some water. Now, here I have 3 bottles. 2 of them are filled with water. 1 of them is empty. Now, I could do this trick just with my bare hand, but to make it a little bit more comfortable, I'm going to use a rubber mallet. So first, let's start with the empty bottle. If I strike this from the top with the mallet, you can see that nothing happens at all, right? Nothing's happening. But now I'm going to take the same kind of bottle, exactly the same, but now it's halfway filled with water. And I'm going to do the same thing. I'm going to strike the top with the mallet. I'm going to do it over here, over a bucket, okay? So in this case, I've got the same bottle, but it's half filled with water. There, what you saw is that the bottom broke out when I hit it in the same way. What's going on? Well, one thing you might think is that when I hit the top, I kind of covered the top perfectly and created a sort of pressure wave inside of the glass. To test that idea, let's use a different bottle that has a wider opening at the top. And what I'm going to do now is I'm going to be sure not to hit it in the middle, but I'm going to hit it on the side. Okay, so let's go over to the side here. And now I'm going to hit the side of the top. So there's no way that a pressure wave could form inside of this experiment. And there you see, we get the same effect. So what is going on? Even though in this case it was open to the air when I hit it, the bottom still broke out. Well, it's because of a vacuum. What happens is that when I hit the top of the bottle, for just a slight millisecond, the glass moves down before the water inside had a chance to move with it. So for that brief instant in time, a vacuum is formed at the bottom. Now, at the top, we've got just open air, so it's 1 atmosphere. Below, we have almost 0 atmospheres because we have that vacuum that formed. And that is a huge pressure difference. That pressure difference means that you have a whole lot of force being exerted on the water, and the water accelerates like a bullet into the bottom of the glass. So that is really showing the power of the vacuum, and I hope that you know from the lecture that it's not the vacuum that has the power, it's the pressure difference. So what we really saw here is the power of the pressure of 1 atmosphere. Now finally, if you do this at home, please do be careful since it involves broken glass. But anyway, the most important point is that it's the pressure differences that we saw, and that these were a crucial part of the history and the foundation of thermodynamics. So there you saw the power of the vacuum, or as I've mentioned, really the power of a pressure differential in action. Guericke's pump was a true turning point in the history of thermodynamics. After learning about Guericke's pump just a few years later, British physicist and chemist Robert Boyle worked with Robert Hooke to design and build an improved air pump. Using this pump and carrying out various experiments, they observed the correlation between pressure, temperature, and volume. They formulated what is called Boyle's law, which states that the volume of a body of an ideal gas is inversely proportional to its pressure. Soon after, the ideal gas law was formulated, which relates these properties to one another. We'll come back to these relationships in another lecture. After the work of Boyle and Hooke, in 1679, an associate of Boyle's named Denis Papin built a closed vessel with a tightly fitting lid that confined steam until a large pressure was generated inside the vessel. Later designs implemented a steam release valve to keep the machine from exploding. And by watching the valve rhythmically move up and down, Papin conceived of the idea of a piston and a cylinder engine. And based on his designs, 20 years later, Thomas Savery built the very first engine. This in turn attracted many of the leading scientists of the time to think about this work, one of them being Sadi Carnot, whom many consider the father of thermodynamics. In 1824, Carnot published a paper titled Reflections on the Motive Power of Fire, a discourse on heat, power, and engine efficiency. And this really marks the start of thermodynamics as a modern science. And 50 years later, along came Josiah Willard Gibbs, who in 1876 published a paper called On the Equilibrium of Heterogeneous Substances. Gibbs and his successors further developed the thermodynamics of materials, revolutionized materials engineering, and turned it into materials science. Recipes were replaced by full understanding and theory, actually laws, which were found to govern the behavior of materials. A crucial development was in the Gibbs derivation of what we call today the fundamental equation that governs the properties of a material, as well as in his demonstration that this fundamental equation could be written in many different forms to define useful thermodynamic potentials. And these potentials lie at the heart of what we will learn in this course, as they define nothing less than the way energy, structure, and even information can be turned from one form into another. Gibbs' formulation for the conditions of equilibrium, that is, when energy flows find a stability, that was an absolutely critical turning point that enabled scientists to determine when changes can occur in a material and when they cannot. Many years later, another scientist you may have heard of, Albert Einstein, weighed in on thermodynamics and famously said, "Thermodynamics is the only physical theory of universal content which, within the framework of the applicability of its basic concepts, I am convinced will never be overthrown." A pretty powerful statement, especially considering it comes from one of the greatest scientific minds of all time. So, what is it that thermodynamics does for us today? What impact does it have on our lives? Scientists and engineers across all disciplines are continually working to control the structure of materials and synthesize them with properties that provide optimum performance in every type of application. They want to identify the relationship between the structure, properties, and performance of the material they're working with. Thermodynamics addresses the question that lies at the heart of these relationships, namely how a material changes in response to its environment. The response of materials to the environment determines how we can synthesize and fabricate materials, build devices from materials, and how those devices will operate in a given application. Armed with knowledge of thermodynamics, we can explain many phenomena in the natural world. With the thermodynamics we'll be learning in this course, we will answer specific questions, such as the following. How do I predict a material's behavior? What sets the boundaries for the behavior of a material? What processes make a material unstable? How is heat related to mechanical, chemical, electrical, magnetic, and other types of work? How do I predict whether and how a material will change in time? What are the limitations of a material? And what is the maximum response of a material to a given force? So the answer to the question, how does thermodynamics impact our lives, is simply, in any and every instance in which we have needed to control the properties of a material or process. That covers quite a bit. So to sum this up graphically, we can visualize a tetrahedron with 4 corners that will label property, performance, structure, and processing. Because in the shape of a tetrahedron, each of these labels has a relationship to each other, it helps us see how they're interconnected. If we change the processing conditions, say by increasing the temperature, then the structure of the material may change. And if the structure of the material changes, then its properties change. It could be the electric properties or optical properties, or simply how stable the materials are and under what conditions they stay stable or not. A change in the properties of a given material will in turn change the performance of a device that is made from this material. For example, if I make silicon using lower temperature processing conditions, then its structure will contain a higher proportion of impurities, which in turn degrade the ability of the material to transport electricity. This leads to a lower efficiency solar cell. But in every type of application, at least every single one in which a material is present, the optimization and understanding of this tetrahedron is critical. Now, in the example I just gave, I referred to temperature as a way to change the processing conditions of the material. But beyond temperature, there are many, many different ways in which a material can be made to undergo a change. The variety of ways in which a material can be changed or affected are what we call thermodynamic forces. These can be mechanical forces, chemical, electrical, magnetic, or many other kinds of forces that have the ability to act on a material. All of these forces are what push or pull on the material in different ways. Thermodynamics addresses the question of how a material changes in response to some condition or some force that is acting upon it. It tells us how to navigate through that structure, property, processing, performance tetrahedron. And as I already mentioned, controlling the response of a material to its environment has formed the basis for many, many technologies. Here are a few examples of specific thermodynamic driving forces and the technologies they've been used to create. With the driving force of temperature, we've been able to make internal combustion engines. With the driving force of the electrostatic potential, we make batteries. With the driving force of mechanical stress, we make essentially any and all materials that are made for load-bearing applications. With the driving force of concentration gradients, we make dialysis machines. With the driving force of chemical reactions, we make what are called piezoelectric materials. With the driving force of surface forces, we create composite materials. And with magnetic fields as the driving force, we've made disk drives. And the list goes on and on and on. Quite broadly speaking, thermodynamics is a framework for describing what processes can occur spontaneously in nature. It provides a formalism to understand how materials respond to all types of forces in their environment, including some forces you may have not thought about or even recognized as a force. There are 2 different points of view of thermodynamics that have been developed over the past several hundred years. First, there is classical thermodynamics, which is the focus of this course. And it provides the theoretical framework to understand and predict how materials will tend to change in response to forces of many types on a macroscopic level. That's the important word here, macroscopic. This means that we are only interested in the average behavior of a material at large length and time scales. The second point of view takes the opposite approach, namely the calculation of thermodynamic properties starting from molecular models of materials. This second viewpoint takes a microscopic view of the subject, meaning that all thermodynamic phenomena are reduced to the motion of atoms and molecules. The challenge in taking this approach is that it involves such a large number of particles that a detailed description of their behavior is simply not possible. But that problem can be solved by applying statistical mechanics to the problem, which makes it possible to simplify the microscopic view and derive relations for the average properties of materials. That's why this microscopic approach is often called statistical thermodynamics. In classical thermodynamics, the fundamental laws are assumed as postulates based on experimental evidence. Conclusions are drawn without entering into the microscopic mechanisms of the phenomena. The advantage of this approach is that we are freed from the simplifying assumptions that have to be made in statistical thermodynamics, in which we wind up having to make huge approximations in order to deal with so many atoms and molecules. Here, I think it's helpful to show a simple example that illustrates these two different types of thermodynamics, classical and statistical. We'll use a piston in this example, and by the way, a piston is perhaps the most classic example used for thermodynamics. It allows us to talk about the relationship between those very same properties that Guericke, Boyle, Hooke, Pepin, and Carnot were all trying to understand nearly 500 years ago, namely the interdependence of pressure, volume, and temperature. So in this piston, we have the usual chamber filled with gas and the piston, which can move in to compress the gas or move out to uncompress it. But in this case, I've also attached a spring around the handle so that when we compress the piston, we also compress the spring, which wants to oppose the force pushing in. If I pull the handle out, the spring will tend to pull it back in. Now, let's assume that this whole apparatus is packed in some type of thermal insulation. So no heat can get into the system and no heat can leave it. If the piston is displaced from its original rest position to some new position and then released, you can see in this animation that it will oscillate. After a bunch of oscillations, the piston will finally come to rest in a new position. And here's the key point. Trying to analyze the motion of the piston in terms of classical Newtonian mechanics, that is, force equals mass times acceleration, will fail. The acceleration of the piston, and thus the force, is not a unique function of its position and velocity. So what's going on here? As you may have guessed, a measure of the temperature in the gas would show that its temperature rose during the process. The mechanical motion of the piston gave some energy to the gas molecules as it pushed back and forth on them. And this trading of energy led to an increase in the gas temperature. But when the gas is at a different temperature, as Boyle would have attested, its volume will change. It will, in fact, expand. And that expansion pushes on the piston, and that is the reason why the piston comes to a new resting place, one that's different than its starting point. Now, we could eliminate the gas completely from this picture, and then we would simply have a piston oscillating on a spring, which is a standard problem in classical physics. In that case, the piston would come to a stop at the same place where it started, and we'd be exploring the exchange of potential energy in the spring with kinetic energy of the piston. But with the gas in there, and in particular, remember, we said that the gas could not give any of its heat away. It will heat up, and the picture is quite different. The piston comes to a new resting place. So what would happen then if we took away that thermal insulation? In that case, the piston is allowed to exchange thermal energy with its environment. And let's also suppose that we immerse the whole piston into some sort of an ice bath so that it would very quickly have its heat removed. In that case, the energy that was going from the motion of the piston into the heating of the gas that energy would now leave the gas and flow out in the form of heat into the ice bath. So in that case, even with the gas present, the piston would return to its original starting position, since the temperature of the gas would remain constant, and there would be no volume expansion. So now we come to the whole point of my going through this piston example, and it comes down to the simple question: could microscopic physics be used to solve this problem when the gas is present and expanding with temperature? To do so, we'd have to track all of the forces on each and every gas molecule as they collide with the container walls, the piston, and one another. If we could do this, then we'd have all of the forces in the system as a function of time, which would give us all the positions and velocities and should, in principle, describe the system. However, if we have a normal piston, a normal size piston, say one we can hold in our hands, then this amount of gas means that we'll have about 10 to the 23rd particles. That's a 10 with 23 zeros after it. So that's the problem and challenge with a microscopic view of thermodynamics, namely that it's simply not possible to solve for. What statistical thermodynamics does is to take this almost unimaginable complexity and begin to simplify it by making many assumptions. For example, one could attempt to use the laws of Newtonian physics, like force equals mass times acceleration, but now include temperature as a kind of new variable that determines force. But this type of approximation is difficult and often only works for one type of problem, but then not for another, different type of problem. Taking instead the macroscopic view, we simply use our equations of thermodynamics, ones we'll learn throughout this course, to describe the interdependence of all the variables in the system. We do not derive these equations and relationships from any models or microscopic picture. Rather, they're stated as laws, and we go from there. The variables are related to one another, and the flow of energy is described without having to know anything about the detailed atomic arrangements and motion. As I already mentioned, most of this class will be devoted to the macroscopic view of thermodynamics, and that is therefore where we shall begin. In the next lecture, we'll cover one of the single most important macroscopic variables of this whole course, namely temperature. And in a few lectures from now, we'll return to this very same piston example. But by that point, we'll be armed with the first law of thermodynamics, which directly relates heat to mechanical motion. Let me end this lecture with one last quote from another famous founding father of thermodynamics, Arnold Sommerfeld. He said, "Thermodynamics is a funny subject. The first time you go through it, you don't understand it at all. The second time you go through it, you think you understand it, except for one or two small points. The third time you go through it, you know you don't understand it, but by that time, you're so used to it, it doesn't bother you anymore." Of course, Sommerfeld was being a bit facetious here, but the point is well taken. Thermodynamics is not always an intuitive subject. We're going to take up the challenge of feeling our oneness with thermodynamics, of making the concepts come alive, and of understanding how they relate to essentially everything we do.